Hello guys, welcome back to our channel. In this video, we will solve a problem from chapter 5, which is the second law of thermodynamics. So we have a problem from Carnot heat engines. A geothermal power plant uses geothermal water extracted at 165 degrees Celsius at a rate of 450 kg per second as the heat source and produces 22 megawatts of net power. If the environment temperature is 30 degrees Celsius, determine A, the actual thermal efficiency, and B, the maximum possible thermal efficiency, and C, the actual rate of heat rejection from this power plant. So in this problem, a geothermal power plant uses geothermal liquid water at 165 degrees Celsius and at a specified rate as the heat source. So the actual and maximum possible thermal efficiencies and the rate of heat rejected from this power plant are to be determined. So in the problem, our assumptions is that the power plant operates steadily, the kinetic and potential energies are zero, and the system properties are used for geothermal water. So we have here properties that we can take a look at our property table, which can be seen at table A-4. So our source temperature is equal to 165 degrees Celsius and our X source is equal to 0. So in our property table, our enthalpy source is equal to 697.24 kilojoule per kilogram. And for our sink temperature, that is equal to 30 degrees Celsius and our X sink is equal to 0. So our enthalpy in sink is equal to 125.74 kilojoule per kilogram. So remember, this can be seen at table A-4. So for our solution, since our analysis is that the rate of heat input to the plant may be taken as the enthalpy difference between the source and the sink for the power plant. So we have this formula, the rate of heat input is equal to the geothermal rate of mass multiplied by the difference between our enthalpy in source and the sink. So plugging in the given value, so we have 450 kilogram per second multiplied by the quantity of 697.24 minus 125.74 multiplied by its unit, kilojoule per kilogram. So solving this equation, we get 257,175 kilowatts. So since we already solved for the rate of heat input, we can now solve for the actual thermal efficiency, and that is denoted by this equation. So the thermal efficiency is equal to the rate of network output over the rate of heat input. So we have 22 megawatts all over by 257,175 kilowatts. So since this is in kilowatts, so we multiply it by 1 megawatts all over by 1,000 kilowatts in order to convert kilowatt to megawatt. So here all the given units will be cancelled and we get 0.0855. So since the thermal efficiency is in percent or in percentage, so we need to multiply this answer into 100. And we get the thermal efficiency equal to 8.55%. So now, since we have the thermal efficiency, we can now solve for the maximum thermal efficiency. So the maximum thermal efficiency is the thermal efficiency of a reversible heat engine operating between the source and sink temperatures. So we have this equation, the maximum thermal efficiency is equal to 1 minus TL over TH. So we have to plug in the given value. So we have 1 minus the quantity of 30, this is actually 30 degrees Celsius, plus 273 all over by 165 plus 273. So we get 0.3082. So again, and thermal efficiency is in percent, so we multiply this by 100 and we get 30.8%. So our maximum thermal efficiency is equal to 30.8%. And now, since we have already the maximum thermal efficiency, we can finally solve for the rate of heat rejection. So the rate of heat rejection is given in this formula. We have the rate of heat output equal to the rate of heat output is equal to the rate of heat input minus the net rate of network output. So that is equal to 257,175 kilowatts multiplied by 1 megawatts over 1,000 kilowatt minus 22 megawatts. So solving all these equations, we get 235.175 megawatts. So our heat rejection is equal to 235.175 megawatts. So this is our final answer.